Hello, everyone. I'm Debbie Hirschfield, Events Director for Rubber and Plastics News and for iTech Tire Show 2020. Welcome to the International Tire Exhibition and Conference organized by Rubber and Plastics News. We're certain you'll enjoy the variety of speakers and panel discussions offered throughout the conference. Our speaker this morning is Troy Anenson, President of CTI. He has a wealth of experience in factory automation projects using Unix and Linux applications, interfaced with a variety of PLCs. He also has several patents. In his presentation today, he will propose an economical method to use rules-based and machine learning image classification techniques to automatically classify tires with visual imperfections. Using images provided by the existing tire geometry systems, tire manufacturers can prevent tires with visual imperfections from being sent to the customer. Let me now turn the discussion over to Troy Anenson. Take it away, Troy.
Thank you, Debbie. My topic today is deep learning for visual inspection and classification of tire defects. On my next slide. So deep learning is an artificial intelligence method by which a computer model can parse inputs and produce outputs in a way that is inspired by how neural networks in the human brain work. With the advent of self-driving vehicles, facial recognition, and surveillance cameras able to automatically detect suspicious behavior, computer vision is quickly developing field, within deep learning. Visual identification tasks that were once the sole domains of human inspectors are increasingly achievable by intelligent computer vision systems. Tire manufacturers have an opportunity to use this technology on top of their existing equipment investment to provide even better quality control. On the next slide. So towards the beginning of this century, many tire manufacturers began investing in tire geometry systems using 3D laser profile sensors. Sometimes these systems were called sheet of light systems or even, line lasers. These sensors scan each sidewall, top and bottom, and the tread of an inflated tire to create a 3D image. The specialized tire geometry software examines each image to detect, measure, and grade any geometry defects along with the radial and lateral runouts. Since these images contain most of the exterior of an inflated tire, why not use them as a second chance to check for visual defects? On the next slide. In a typical tire factory, tires are fully inspected inside and out prior to final finish testing by a specialized workforce of tire inspectors. Downstream from this inspection, tires may be rejected or flagged for further inspection by any final finish test machine. And this could be, for instance, a tire uniformity machine or dynamic balancing machine or even an x-ray machine. Otherwise, they get sent directly to the warehouse without additional inspection. So therefore, it's possible that tires can suffer visual damage by their handling after they were fully inspected and end up in the warehouse. These tires eventually get installed on vehicles where the customer can notice a visual defect, and that could reflect poorly on your quality control. So for a small investment, a tire factory could add visual inspection software to further examine its already collected 3D laser profile images. This allows the tire factory to gain even more value from its prior large investment in tire geometry systems. On the next slide. So tire geometry systems are typically located on a tire uniformity machine or a dynamic balancing machine, or they could even be on their own dedicated machine. But on the majority of these machines, the tire is inflated and rotating at 60 RPM or 1 revolution per second, And typically they have three sensors covering the two sidewalls and the tread, and they collect measurement data in 1 revolution or 1 second. The tire geometry system provides typical geometry measurements: bulge, depression, lateral runout, radial runout, wobble, etc., to the machine's control system, which then, uses them to provide final grading results about each tire. And on the next slide, so like I said before, many of these geometry systems exist today with 3D laser profile sensors, providing at least 1,000 profiles per revolution and containing a field of view of at least 75 millimeters of tire data per profile. Newer sensors, such as the GoCater 2530 from LMI Technologies, can provide over 4,000 profiles per revolution. Other sensors, used mostly for the tread measurements, provide a wider field of view, up to even 400 millimeters per profile. Obviously, acquiring more profiles per revolution greatly increases the capability of the visual inspection software to detect even the smallest defects. But tire geometry data collected at 1,000 profiles per revolution from the older sensors, they can still detect many of the larger defects. So you don't necessarily need the latest tire geometry lasers to find benefit from visual inspection software. The image data from these 3D laser profile sensors is stored for each tire so that they can be reviewed later if the downstream final tire inspectors or quality assurance people in the plant find fault with any of the geometry measurements. The vision inspection software would have access to these stored images as well. And on the next slide, so the only visual defects measured by the tire geometry systems are basically bulges or depressions on the sidewalls, or bumps or dents in the tread. These are typically caused by tire construction issues, and that's what the tire geometry systems were designed to look for. Other visual defects appearing in the tire geometry images go undetected by these systems because they're not designed for that. So some of these defects that go undetected could be caused from contaminated tire molds or rubber not flowing correctly in a mold, or they could be defects from damage due to tire handling equipment, or even damage from improper processing by machines upstream of the tire geometry system, such as a white sidewall grinder or buffer, as they're also known, or even trimming stations, or grinding force or runout grinding on a tire uniformity machine. In the photos on this slide, you could actually see an actual visual defect. And what we've shown is a picture of it provided by visual inspection software, and also a real photo of that same defect. And that typically is a defect from a contaminated tire mold. On the next slide, so this is where the visual inspection software can help. Visual inspection software processes the high-resolution laser images from the tire geometry systems in a completely different manner, focusing on sharpening and flattening the image to provide the clearest picture. It detects and classifies any visual defects found in the tire geometry images. It could also find objects such as the DOT code or the tread wear indicator bars, deep in the tread grooves. Such software could provide higher quality assistance to a human inspector, or sometimes called the tire classifier, or even replace the most mundane aspects of their work, freeing them up to process many more tires. You can see an example of a flattened and sharpened image by visual inspection software in this slide, and you can see how readable the DOT code is. And on the next slide, so in the beginning of this proposed solution, the visual inspection software provides its results in high-resolution images to the existing human-operated final inspection stations, or tire classifier stations, as they're also known. These stations would make use of a large, wide touch panel to display a tire's visual inspection images with all the potential defects clearly identified. And then with the ability to pan and zoom on this display, the human inspector can manually classify each defect by selecting the appropriate defect and picking a classification from a drop-down list. They could even look for other visual defects that were not found by the software and identify those and classify them in the same manner. They would also have the tire available to help in this process. So this feedback from the tire inspector by classifying each defect serves two purposes. One, obviously, it's going to help improve the quality control in your manufacturing process. But two, this feedback can be used to train a deep learning model. And a deep learning model, it would learn to detect and classify these visual defects with high precision, becoming adept at the first purpose, of flagging tires for rejection or repair and removing that task from the inspector. And on the next slide, this is a similar slide to the first one. It's missing a little detail, but there it goes. You can keep bringing in detail. There we go. I didn't know that was like that. Anyway, so let's review what I just said about how this could work. So you have a finished tire machine, as you see at the beginning here, number one. It's got the tire geometry system. It's gonna, do its geometry testing on this tire, and the tire will leave the machine, and the visual inspection software will then, identify any defects that might be there. And as the tire progresses downstream, at a decision point, its intelligent material handling software, it could, query the vision inspection system to find out that there were potential defects, and it could get diverted to the final inspection station or the tire classifier station in some plants. So the inspector then classifies, that defect, and that feedback is used to train a deep learning model. After the model is trained, the software then identifies and classifies the defect. So in that case, the tire, once you have a deep learning model and that's in use, the diverter, or that can actually divert the tire directly to a repair area or a reject area based on your classification or the classification of the deep learning model, and the final inspector can be and those tires can bypass the final inspector altogether. So in the next slide, there we go. So we'll talk a little bit about deep learning and image. So one natural application of computer vision within deep learning is image processing. Within image processing, you have two common techniques: object detection and image classification. Object detection allows computer models to separate parts of images into background and foreground, and the foreground parts are then analyzed, allowing for automatic detection, location, and classification of objects within an image. Image classification is when computer model analyzes the whole image and then makes a decision. For instance, if this is a photo of a cat or a person, These two techniques can be applied to visual tire inspection, whereby a computer model can input images from tires and output a list of classified defects from these images. And on the next slide, so here's a slide of a sidewall of a tire showing another visual defect, that wouldn't be found by tire geometry systems, but with visual inspection software, we could highlight this defect and even classify this defect once a deep learning model has been trained. And this defect looks like, again, would be caused from like contaminated tire mold. And on the next slide, so a better example of object detection would be where you could detect like a DOT code on the sidewall, assuming it's within your tire geometry images, which many of them are nowadays. Or you could even find the tread wear bars deep in the tread grooves, as you can see in the image in this slide, where we've highlighted the tread bars, which then could be measured from this tire geometry data. And on the next slide. So before the deep learning model is trained, visual inspection software uses rule-based image classification algorithms that are specific to finding defects that meet its pre-programmed criteria. Any defects beyond a predefined surface area or volume threshold are highlighted in its resultant images. Defects such as pits or blemishes from, carrying mold contamination, or gouges or similar damage from tire handling equipment, or unwanted pin vents or flashing, and damage from improper processing by upstream equipment such as grind appearance issues, they can all be detected using smart rule-based algorithms employing statistics and thresholds to differentiate pass from fail. This is similar to the way the tire geometry systems, look for bulges and depressions. So in this image, you can see that the vision inspection software found a pit in the letter R. And the predefined rules in this case that it used were established to flag any area 0.4 millimeter below the sidewall surface as a defect. So rule-based software algorithms can provide good results for identifying many visual defects, but these have an accuracy rate of only high enough to assist with their classification by a human inspector. So that, meaning basically that sometimes, a rule-based algorithm can get fooled by tire lettering or artwork, especially with the, fancier sidewalls that are being generated these days, and all the different artwork and embossing going on, and then, the rule-based software can just miss some actual visual defects. So that's why we need the help of the downstream tire classification or tire inspector. And on the next slide, so in contrast, a deep learning model would train itself from the defects confirmed by the visual inspection images and classified by the tire inspector, as I mentioned before. So once the accuracy of this model is validated, the visual inspection software is updated to begin using it to detect and classify defects without the assistance of the final inspector. It's common to report accuracy of a deep learning model compared to the accuracy of a human doing the same task. It's not expected that either will be 100% accurate, but these models, these deep learning models, often outperform their human counterparts. The availability of labeled data, i.e. classified defects, in this case, to train these models is one of the biggest limitations industries face when looking to implement deep learning. Input data labeling as a human task, it is a human task, and it can take armies of labelers dedicated to the task. If labeled data is not being produced as part of a normal production process, it can be prohibitively expensive to generate. That's why tire manufacturers have a unique opportunity to bring this transformative technology within reach by simply making the commitment to capture data as part of an existing inspection process. Multiple tire factories within the same organization can share their captured data, training the deep learning model, even faster and even more accurately. And on the next slide, so outside of detecting and classifying visual defects, the visual inspection software has additional image classification object detection algorithms, giving it even more value. Such algorithms could locate and read the DOT code on the sidewall, as you can see in the image provided on this slide. And it can even, measure the amount of rubber removed by force or run-out grinding on a tire uniformity machine, or even measure the height of the tread wear bar indicators deep in the tread grooves. Once the deep learning model is trained, it could even run directly on the tire geometry systems, classifying any defects, reading the DOT code, measuring the height of the tread wear indicator bars, and even checking grind appearance. It could make those tasks part of the final geometry grading results. It could even call for an extra cleanup grinding from the machine controller if grind appearance shows it is needed. Obviously, I'm talking about tire uniformity machines, with grinders or optimization, as it's called, to improve the force or the run out of the tire. On the next slide, since this is software, it can be updated and retrained to find new problematic visual defects or to support new images from updated 3D laser profile sensors. Now, think of it like Tesla's autopilot feature. Even the older Tesla models can be updated to the latest autopilot features, including their latest deep learning models trained on the feedback from the ever-increasing amount of Teslas on the road, with the future hope that any Tesla would be capable of full self-driving. And on the last slide. So in conclusion, using images provided by the existing tire geometry systems, tire manufacturers can prevent tires with visual defects from reaching their customers. It was a big investment to add tire geometry testing using 3D laser profile sensors. However, only a small investment in visual inspection software is needed to detect and classify visual tire defects with high precision. Rule-based software algorithms can provide good results for identifying many visual defects, but with confirmation and classification of those defects by the existing final inspectors or tire classifiers, as they're known in some plants, an expansive data set can be created for training a deep learning model to detect and classify defects without the aid of the final inspectors. So this data set guarantees increased quality from the plant floor to the tires on the road. And that's it for my presentation today.
Thanks, Troy. That was a really insightful presentation. I would also like to thank our audience for attending this session of iTech, and thank you to our sponsors for supporting iTech Virtual 2020. If you want to revisit this session or any others from the conference, they will all be available on the Rubber and Plastics News website, rubbernews.com, after the event is completed. If you would like to purchase papers from this and any other sessions of iTech, visit itech-tireshow.com to do so. Don't forget that you can also connect with your colleagues here through our virtual networking program. This can be found on the left-hand side of your screen. Simply click the Meet icon to start connecting with your fellow iTech attendees. Thank you for joining us today.